we can see that they are tetrapyrrolic derivatives because we have these common patterns on all these structures. So if now we get onto the structure of the phthalocyanines, which are artificial porphyrinoids, if you just put like that 4 pyrrole units and you relay them to each other, this is the basic porphyrin core unit. This is the basic one. So it's not a phthalocyanine yet. If you want to have a phthalocyanine, and we do want this, we are adding some nitrogen atoms and benzene rings like that. So you can see the difference and the analogy between these molecules. And then our jobs, because we are chemists, is to play with all the structural variation, which are nearly infinite, that we can implement on this core. So we can make a lot of variation with the metal. This is all the metals that have been inserted so far into phthalocyanines. Depending on the metals, it's possible to have some actual substituent. And we can also play with substituent at the periphery of the core. We can put 3, 4, 8, even more, also even less, in what we call the peripheral position or the non-peripheral position. So this is really a situation of nearly infinite possibility. And this is going to help us, to allow us to modulate the solubility and the aggregation, which is something that usually we don't want. We also are going to tailor the photophysical and photochemical properties, so it can be the maximum electronic absorption, the fluorescence, the single oxygen generation, the redox property. We can introduce some chemical functionalization. So you can see that we have really a lot of possibilities. And there are even more exotic and different structures that are related to this phthalocyanine. So then we are speaking about the porphyresins, the subphthalocyanine, the double decars, etc. So you can see that it's really an extremely rich chemistry. So just now we are going to focus a little bit on the importance of the substitution patterns. I will give you 2 completely fundamental examples, but which for me are always extremely striking. This is a series of 4 phthalocyanines that we have been synthesizing in the lab. And you can see that it's all the same metal at the center of the microcycles. They all have 8 acyl chains, but the difference is the grafting atoms, which can be a sulfur, an oxygen, or a grafting function, which is a sulfonyl here, and the position for this one. And what we are doing, the purpose of this work was to investigate the effect of the substitution patterns on the substitution position, the electron withdrawing versus electron donating substituents, and the donating force. And this is indeed what we could observe. You can see that we really have an amazing difference only in the maximum absorption of this derivative, depending just on this position and grafting function. And we also have difference in terms of singlet oxygen generation and phosphorescence. This example here for me is even more amazing because you can see these 2, you can imagine that there is a big difference between these 2 structures right here. We indeed have 55 nanometers of difference in the maximum absorption, but in this case, we even have the same substitution pattern, which is S-alkyl, octa in non-peripheral position, but the bulkiness of the terbityl groups right here are inducing a distortion of the microcycle, and this distortion is inducing this shift of 55 nanometers, which is extremely elevated, extremely important, regarding the fact that anyway, this is formally the same substitution pattern. And this has been confirmed by some calculations. So as you can imagine that it's important to have good synthesis access to different substitution patterns. And we have been working on this because unlike for porphyrins, which is, I would say the simplest version of the family, the porphyrin chemists, indeed, they can prepare porphyrins with 8 different substituents. And this is what Clifford Leslov said in a congress 14 years ago in Roma. Lesnov is one of the father and the kings of the chemistry of phthalocyanine. And he said when such scientists can synthesize a phthalocyanine with 16 different substituents, our problems may be solved. And the problem indeed is that we have 10 to 16 possible compounds. So you can see that this is a huge possibility. You cannot mix only substituent and see what is going to happen. So in this cover of the Journal of Porphyrin and Phthalocyanine, which is the reference journal of the field, we tried, it was edited by Professor Sisesquioxane, and in the cover, this is a phthalocyanine which cannot exist. It was just a way to represent all the substituents that were part of this issue, but we are absolutely not there yet. This is only a piece of art. So what was existing a couple of years back, a few years ago, was the substitution that we call A4, because phthalocyanine have 4 subunits. So it was when you have everything on the same 4 units of the phthalocyanine. We had the A3B, the ABAB, and the AABB, and they could be all obtained by selective or statistical methods, knowing that even with statistical methods, you can control something if you play, for example, with the ratio of the starting compound that you are introducing in the reaction. And what we did is that we developed the first and only, so far, ABAC derivatives. I'm not going to enter into the detail here because it's not a talk about the chemistry of phthalocyanine directly. But anyway, even this is something which still has some synthetic limitation, because we have to use this quite specific precursor, which is prepared in very harsh synthesis condition. So it's not compatible, to have all the substituents that we have here. So we are progressing on this, but it's not done yet. There is still a lot of work to do. And just now I'm going to show you what is for me an anecdote, and which is quite representative of the what is the job of researcher, I would say, because I had the possibility to make a stay in Canada during 2 months in the summer 2014, and I just my purpose was to prepare a compound, a type of phthalocyanine. And when I was thinking about the synthetic method for it, I realized that I had the possibility to access ABCD phthalocyanate. And I was thinking that if anything happened, I just need to write it somewhere. So I just sent this postcard to my father. And then coming back to the lab and everything, I didn't get the possibility to really work on this synthetic strategy. And 2 years later, it was published by another group, exactly with the same idea. So this is, I would say, extremely representative of the way that sometimes we are thinking of something, we cannot do it, someone else is going to do, but anyway, the science is progressing. So if we come to the core of the talk, let's see why we are going to put the phthalocyanine into nanoparticles. And the fact is that phthalocyanine here, they have a lot of different properties, as we mentioned a little bit already. So it can be singlet oxygen generation, fluorescence, redox property, magnetism. They have an intense color, electrochemical behavior, and then they are used for different applications. So the first, of course, coming to mind because of the intense color is the use as dyes. It can be printers, essentially. They are also widely used in PDT, which is my main core of research, imaging, also as catalysis in energy topics, which I am not that much dealing with it. And the thing is that when you combine this phthalocyanine with nanoparticles, you get either new properties or you can improve the existing properties. And then our job as the chemist is then first of all to design the nano object. This is the first step, to decide what is the final target, what do we want to obtain at the end in terms of nanoparticles. And then, because the chemistry of phthalocyanine is not that simple, we need also to design then the phthalocyanine itself and the synthetic strategy. Because what I say, it's always easy to draw a molecule on paper, and doing it in reasonable yields and quantity is not always the same thing. So this is a two-step process. And the first example that I'm going to give you is the use of phthalocyanines that have been used to electrochemically reduce carbon dioxide reductions. So the thing is that this is a work in collaboration, conducted by Unitisti in Gebze and Marc Robert in Paris in collaboration. And the purpose is that, the reduction of carbon dioxide into carbon monoxide or in other chemical feedstock, like for example methanol, is something that is really important nowadays. And a strategy is to use catalytic inks. And what so far was working quite well was to use porphyrins methylated with earth abundant metals. Other complexes also are working with earth abundant metals. This is the idea of using something that you can find easily. And then to support this complex onto thin porous carbon nanotubes to be able to work in aqueous conditions. Of course, you always prefer, especially when you are dealing with an environmental or energetical issue, to work in water, to be able to work in water. And what was designed is this molecule. So the idea was to have this cobalt catalytic center right here to have an appropriate solubility, because if you want to purify the phthalocyanine, and phthalocyanine itself with no substitution is something which has a very, very poor solubility. So for the purification, especially when you have an asymmetric substitution patterns, this is a problem. So you need to introduce groups that are allowing you to perform active purification. And the presence of the trimethyl ammonium substituent here in this position is first of all giving an overall electronic pattern on the phthalocyanine itself. And the most important also is that thanks to this positive charge here, we have the possibility, because this positive charge is going to interact with the doublet of electrons on the oxygen of the carbon dioxide, and it's going to maintain the CO2 molecule close to this catalytic center. And this design, is quite elaborated, I would say, but again, it was possible only then to perform the good catalytic experiment only after loading either on carbon black powder or on carbon nanotube, and to form this carbon paper cathode. And the result of this is that compared to the previously existing system, it was much more robust. It didn't decompose that easily during the course of the reduction of the carbon dioxide itself, because this is often the problem. And then we could publish it in a quite good journal. On the completely opposite side, still catalysis, but this time oxidation, phthalocyanine can act as methane oxidation catalyst. So of course then the design is not going to be the same, but this is something that is quite useful. And this is completely different type of phthalocyanine. This is what we call minithido. So we have dimeric iron phthalocyanine. So the basic structure of it is to have two phthalocyanine core right here of iron connected by a single nitrogen atom. So this work were in collaboration with Alexander Sorokin in France, in Lyon, and also still Unitisti. And we knew when we started to work on this specific work, we knew that the minithido dimeric iron phthalocyanine are extremely efficient oxidation complex, that they can oxidize methane at room temperature, but we were still missing some data about the oxidation process and mechanism itself. And for this is then the role, I would say, of synthetic chemists also, to design structures that are going to allow you to understand what is going on, And what we did is to design and prepare this asymmetric structure with one phthalocyanine non-substituted, electron rich, and this one electron poor, substituted by sulfonyl substituent right here. And we did it with a tetra substitution and octa substitution. So we had these two derivatives, and the idea was to check where is from the active oxidative species, because you are using, of course, an oxidant. It can be water peroxide or terbityl peroxide. And what we could show with some calculation, also not some calculation, with a lot of calculation, that the hydroperoxoxidant was preferentially binding on the more electron-rich ion side, so the non-substituted one. And this is also the place where the oxo species is formed. So this was getting an insight of the mechanism of it. Then, to be able to check it experimentally, what was done is to really test the metal oxidation in water. And of course, these molecules, just to show you the structure, these molecules, they are not soluble in water. So you cannot just put them in water because they will precipitate and then nothing is going to happen. So for this, you have to support them, and they were supporting onto silica particles. And for this, we were using the homoleptic structure, which means that we had the same substitution pattern on both phthalocyanine of the complex. And three complex were prepared, were used. One with electron-rich substitution, thanks to the only terbityl substituent at the periphery of the phthalocyanine. One with nothing, and the electron-poor substitution pattern with the sulfonyl terbityl substituent here. And we could show, after this support onto silica particles, that this is the metal oxidation was following what we guessed with the calculation, that we had a better efficiency for the electron donating only terbityl substituted complex, then a little bit less good with the unsubstituted phthalocyanine, so just nothing on the microcycle. And then the one with the SO2 terbityl substitution were the less good one. So this was really giving new insight on how we can optimize again the design of silica particle supported oxidation catalyst. And now I'm going to come to what is more, I would say, the core of what I am doing, I would say, every day. It's using the phthalocyanine for photosensitizer, but for photodynamic therapy. So before getting into the detail, I just would like to give some precision about the vocabulary, because I can see in some papers that there are sometimes some confusion between what is what, I would say. So what we call a photosensitizer in this field is a system, so it can be molecular, it can be nano, which when you illuminate, irradiate, excite it, is generating singlet oxygen, and possibly also other reactive oxygen species. So this is what is the photosensitizer. And then we have this singlet oxygen which is generated, and this is then a photodynamic application, a photodynamic process. And any photo-induced utilization of singlet oxygen is something which is photodynamic. And you can use the singlet oxygen to kill some cells. So this is going to be photodynamic therapy. It can be also to perform some oxidation catalysis. So this is photocatalysis, which itself can have different purposes. It can be to destroy some pollutants. So this is remediation, and this is destructive. And this can be also used to prepare something, because we are making, synthetic chemists, we need to perform some oxidation from time to time. So you can use singlet oxygen to do this. It can be also for drug delivery purpose. And in this case, it's like the trigger drug delivery. And all of these things are photodynamic application, but they are not all photodynamic therapy. Because I can see sometimes some paper with PDT. Sorry. Okay, I just continue. I think someone. So what is important is, when you are making photodynamic therapy, it means that at some point you have some cells in the study. And when I speak about cells, it can be cancer cells that you want to kill. It can be cells of vasculature, and in this case, you are not treating cancer, you are treating age-related macular degeneration. And you can also be killing bacterial cells, and in this case, it is antibacterial photodynamic therapy. So how is it working? Anyway, to get into the detail, you have the photosensitizer in a fundamental single state. This is the Jablonski diagram. At some point, we always put it out when we are speaking about PDT. It's excited at the wavelengths of the absorption, and a molecule or nanoparticle which is excited usually at only one purpose in life, it is to get back to the fundamental state. And for this, it has different possibilities. It can emit some fluorescence, which is something that we want a little bit, but not too much. And it can also get, thanks to the intersystem crossing, it can go to the excited triplet state from the excited single state. And from this excited triple state, what can happen? Again, several possibilities. Could be the emission of phosphorescence, which is something that we don't want for PDT, or it can exchange energy with the surrounding molecule of oxygen. And with this exchange of energy, the surrounding molecule of oxygen are getting into their triplet state. And this is into the singlet state. And this is the singlet oxygen. And this singlet oxygen is extremely reactive. It's a powerful oxidant, and it has a short time. So it's going to oxidize everything it can, but in a very close localization. And this is how we have, this is the two reasons why we have selectivity when we are doing some PDT. We first of all choose where we are putting the light. We are not illuminating the full body, for example, after the injection. We put the light only where we want to have an effect. So this is what is represented here. You inject the photosensitizer. This is the tumor. You wait to have an appropriate accumulation at the site of action, and then you illuminate only at the site here. You are not going to do it everywhere, and then you have a disappearance, in this case, of the tumor. So this is the first selectivity that we have. And the second one, which is more on the absence of side effect, is due to the short lifetime of the singlet oxygen. It means that there is no time for this singlet oxygen and also the other reactive oxygen species to go to damage something else in the body, because anyway, it's only, it's already not existing anymore. So this is a huge advantage of the other cancer treatment modality, for example, which we all know have very bad side effects. So this leads us to the importance of the design of the photosensitizer. We know, you know now that PDT is a three-partner process. You have guessed that. Otherwise, we need this photosensitizer, we need the light, and we need the molecular oxygen. So if one of these three partners is missing, you cannot do PDT. And for this, to make PDT, and as chemists, again, we are interested in the photosensitizer, there are now second and third generation of photosensitizer. And this is the list of the properties that we want for this photosensitizer. The first one is we don't want something which is toxic in the absence of light, because if not, we wouldn't be doing PDT, we would be doing chemotherapy. So this is not our purpose. We want water solubility because it's biocompatibility, but we wanted also amphiphilic to be able to enter the cells. We want a good near-infrared absorption, and I'm going to get back to this. of course, a good signal chain generation, not too much photo-bleaching, good cell uptake, tumor targeting, sometimes some dual effect, and then imaging intervention, and the use of new excitation mode. And this, I really call it like the list to Santa Claus, because it's difficult to put everything on the same photosensitizing system. And this is such a field of research that it's even possible to edit a full issue of a journal of the European Society of Photobiology. So that I had the pleasure to guest edit this issue 2 years ago, and you can see that there were really a lot of different topics in it. And it was just about the design of photosensitizer, the engineering, molecular and nanoengineering of photosensitizer. So this is really only the job of the chemist, but there is a lot of things to do. So just to get back to what I call it the Graal in PDT, this is the near-infrared excitation. There are two reasons why we want to use near-infrared wavelengths to excite the photosensitizer. First of all, is that the longer the wavelength, the deeper is the absorption into the tissue. And tumor, they have a thickness. They are not always at the surface. So this is something important, first of all, for this reason. And the second reason is that we have what we call the phototherapeutic windows. And it's something where the biological chromophores are not absorbing, because it's not good to excite also oxygen, hemoglobin, and melanin, because this can induce side effect that it's always better to avoid. And at near infrared, what we call here near infrared wavelengths, we are not touching them. Water is not completely boiling there yet, let's say. So this is why we want to excite at this wavelength, and this is why phthalocyanines again are absolutely the best. So this is a comparison of different porphyrinoids. This is a porphyrin, this is a chlorine, the bacteriochlorine and the phthalocyanine. The bacteriochlorine here is better than the simple phthalocyanine, but this is really complicated to make bacteriochlorines. They are not that well stable. So anyway, phthalocyanine are better. And anyway, we can modulate the phthalocyanine. And this is, if you want to know more about that, this is a review that we have published quite recently. And this here you can see that when I said that phthalocyanine are good for PDT, it's really because a lot of them are already in clinical trials. So this is a liposome formulation, so something which is nano. This is more in Russia. This one is from China. This one is in the US. This one is used in a lot of places. In my opinion, it's one of the most clever design of the phthalocyanine for biomedical application. And then again, why are we going to use this beautiful phthalocyanine for anti-cancer treatment? Because this is what we are discussing here. And this is due to what is called the Enhanced Permeation and Retention effect. And what is it is that the vasculature, the healthy vasculature in an organism is something that is not permeable. So if you inject something in the blood circulation system, it's going to go around. But the tumor is something which it's a quantity of cells that are dividing really quickly, and for this they need a lot of energy, and to attract this energy, the tumors are building usually their own vasculature system, and they are doing it very quickly, and so they are not doing it very properly. This is like, when we do something quickly, it's not done very well. And this is the reason why the vasculature of tumors is leaky with some holes in it. And the immediate consequence of this is that nanoparticles, they can selectively exit to the tumor tissue because of the leaky the leaky nature of the tumor vasculature. So it's a kind of a mechanical tumor targeting of the nano object. So this is represented here and here. And this is Maeda, who just really demonstrated this. It was 40 years ago, but this one 35 years ago. And this was a review on all the what you could demonstrate on it. And when I say that it's really something important, that means that the European Union even was building a specific technology platform on it. So there is the European Technology Platform on Nanomedicine. I have been organizing together with Professor Hassan the Nano Cancer Day, which is on the 2nd of February every year. Because the Cancer Day is on the 1st of February every year, it's now the Health Tech Cancer Day. And this is really showing you how the nanotechnology is important in cancer treatment. But then, of course, nothing is perfect. And this study 4 years ago was starting to put something in question when the analysis of nanoparticles delivery to tumor was really detailed. And then it started really like a buzz, I would say, especially in chemical and engineering news. And the title, very catchy, was Does Nanomedicine Have a Delivery Problem? So it was really like, have we been, the researcher, getting too much focusing on it? Is it really working? So then a lot of people were starting to give their opinion about that. Is it really okay, sufficient for curing cancer? And what I really like in this editorial is that it's remaining that anyway, all the cancer and all the tumor are different. I mean, one patient, it means one different characteristic, even if it's the same cancer as someone else. And there are any reason for nano, reason to use nano, because we have this EPR effect, which is heterogeneous, so it's not going to work for everybody, but it can be working, is anyway working in some extent. And the other reason is that, even if it was not the first one at first, is that nanoparticles we can consider their platform. So it's not only the things of the EPR effect, it's also that then you can have platform to combine different drug, for example, different imaging technology, and this is also extremely interesting. So this is what do we do with that? We have different approach to include the phthalocyanine nanoparticles for PBT, to use this platform and also the EPR effect. So this one was a collaboration with Hong Boon Lee in Malaysia and Maria Vicente in Spain. And they contacted me because they wanted a phthalocyanine, because they wanted near-infrared absorption, and the idea was to graft it on polyglutamic acid nanoconjugate. So then I had to design a compound and to define a synthetic strategy. So the idea was to run this A3B substitution pattern to have one function able to be grafted on the nanoparticles and to have something which could be, as we said before, purifiable quite easily. So this is the chemistry that we did. We isolated this compound, sent it to Malaysia, and it has been grafted on the existing nanoparticles. Because this is also, when I speak about the synthetic strategy, you then need to define the synthetic strategy of the phthalocyanine that you're targeting and also how you are going to make the nanoparticles. So in this case, the phthalocyanine was grafted on an existing nanoparticle right here. And a nice particle size distribution was observed. Solubility in aqueous media was observed, more than the reference compound. Good singlet oxygen generation was also observed. And then the test against breast cancer cell could show that, first of all, this is what you always check first, that there were no real dark toxicity. So this is really what you wish to have. The zinc phthalocyanine alone by itself anyway showed to be a little bit toxic, but this was the reference compound. And then the phototoxicity was checked, and we could show that our system was exhibiting phototoxicity. Less than the zinc phthalocyanine alone, but then when we check the light-dark toxicity ratio, we could show that anyway at appropriate concentration, because of the intrinsic cytotoxicity or the unsubstituted zinc phthalocyanine, this system was much better, and then avoiding the few side effects that could have been observed with the zinc phthalocyanine alone. Further experiment in vivo this time showed that we had a good system, cleaning the metastasis with no cardiovascular toxicology. So this was something that was really satisfying for this preclinical test. We have been also developing a completely different strategy, still to have phthalocyanine nanoparticles. This time, the idea was to prepare, and I'm going to say it only once, Silsesquioxane nanoparticles, and these nanoparticles are usually prepared from a bis-3 alkoxysilylated organic precursor, so there is no inorganic silica source in it. And as a result, and it self-condensates, and as a result, the organic parts represent 50 to 80% of the structure. And it can have a periodic and mesoporous structure. We will see that it depends on the derivative that we are using. So this was in collaboration with Professor Becassin, Jean-Olivier Durand, and Magali Garibobo in Montpellier, in France. And the idea is to provide propagulated derivatives that can be clicked with this 3-ethoxysilane compound to obtain this kind of generic derivative that can self-condensate to obtain then nanoparticles. So this is what has been done first, and this was with a comparison with porphyrins. So the nanoparticles have been prepared. We could see that we still have the near infrared absorption, which is retained a little bit more like the potatoes. It's normal, it's a kind of solid state. Good distribution size also, everything was nice, but then came for me at least the big disappointment is that the phthalocyanine-based nanoparticles were not really efficient in terms of photodynamic direction. They have been tested also in photoacoustic imaging, and then the results were beautiful. But when we were just checking the photodynamic therapy with 1 or 2 photon excitation, it was not that good. So the conclusion was that we have anyway systems that are theranostic. We could make some 2 photon imaging, but anyway, the porphyrins were better. So this is something that, as a phthalocyanine enthusiastic people, I didn't like that much to hear. And then we continued on different systems, not that different actually, because if you look at this structure, we have 4 propargyl units on the peripheral position, a second one on each subunit right here. So this was this guy right here, giving this after they click also with the 3-ethoxysilane derivative, which is this molecule that could self-condensate into this nanoparticle. And just the fact to use octa-substituted derivatives, phthalocyanine, instead of the tetra, we had a much more porous nanoparticles. And we could then perform at this point really efficient PDT, especially when the excitation was at the maximum of wavelengths of the phthalocyanine, and even with the pulse laser, so completely in the transparency window, which is the other name of the phototherapeutic window, so as far as 760 nanometers and also beyond 800 nanometers. The other thing that was successful is to introduce AcRNA into the pore of the nanoparticles, and then to obtain a translation effect upon the irradiation. So this was a combination then of photodynamic therapy and photochemical internalization. So this was a nice result. So the conclusion of this work is that phthalocyanine are really powerful molecules. I know that I am not really impartial because I like them a lot, but they are anyway, that's a fact, powerful molecule for different applications. And there is what I call the nanoparticle empowerment. So we are open to collaboration if anyone wants to benefit from this very nice molecule. So because research is a teamwork, I want to thank all the current and past students, postdoc, project member. I hope I didn't forget anyone. We could attract Erasmus trainees from abroad, so who are coming usually during summer to make an internship with us. So they also have contributed to this work. I want to warmly thank the colleague from Gebze, Phthalocyanines, Ashiguldirek, Devri Matila, and especially Imitisti. I want to thank all the structure that have been giving some award, which is always motivating. So Tuba, Bilim Academici, and the Mustafa Parla Foundation. The Embassy of France also is giving some money, and of course Tubifac. All the collaborators, I mean, not everybody is there, but research is a collaborative work. So this is what makes its richness. So I want to thank everybody here and all the people that are not here also. And just before asking if you have any question, I would like to attract your attention to the Journal of Porphyrin and Phthalocyanine, which is the journal in which you can publish works on this, and it was very nice to edit together with Professor Pebeloniokong and Penelope Brothers this series of 4 issues last year of GPP that were highlighting the role of women in porphyrin science. We are aggregating all the contribution into an upcoming book. I really believe that we still need to promote the role of women in science. This is a map of the proportion that you can see in the world. So Turkey is not doing that bad compared to France, for example. So this is something to do, and anyway, you can consider the journal for your regular submission. And because I am also an associate editor at RSC Advanced, I could prepare 2 editors' collection, one on photodynamic therapy and another one on phthalocyanine. So you may have a look at them if you want to know more about the topic. And I can now just thank you for attention. And if you have questions, I can take them. How are you?
Hocam değerli paylaşımlarınız için çok teşekkür ederiz. Herhangi bir soru var mı acaba? Soru varsa alabiliriz.
Benim bir sorum var.
Tabii hocam, buyurun.
Fabienne hocam, çok teşekkürler. Thank you very much. It was very nice talk. Congratulations on your new position.
Thank you.
My question goes back to first part of your talk. Recently, I have read that the article on CNN News that the dioxane is very dangerous and cannot be removed from the wastewater, I mean, the drinking water.
Which one?
Any of your dioxane, 1,4-dioxane. Any of your phthalocyanine catalyst can help to solve that problem. I mean, I don't know if you're aware of that problem or not, but it could be a good, one of the good research area, because many people are trying to remove the dioxane from the drinking water, but could not succeed. But of course, if you can convert them into some other more soluble or separated particles, could be help.
We can try. Yes, we can try. I mean, there are water purification systems based on this. Usually the idea is to immobilize the photosensitizer in like a filter or something. The water that you want to clean is getting full. Usually the idea is to use also sunlight, so phthalocyanine are good for this also. And then there is the possibility to oxidize the dioxide. So this is something that can be tried. It will oxidize also other pollutants if there are other things. It's not going to be specific to dioxide, but I'm sure something can be tried.
How do those materials are largely producible? Do you have very complex molecules, very large, big, and is it easy to prepare?
Well, it depends. I mean, sometimes we make things complicated just for, I would say, for the beauty of science and of the synthesis. But when really we want to do something that is supposed to be applied, then we pay attention to do something simple and scalable. So we have already made grams of phthalocyanines. I never try to make kilograms, but people do. So, but this is something that we will take into account anyway.
Okay, thank you.
Welcome.
Başka soru var mıydı acaba?
If anyone has something, I mean, my email was on the first slide, or you can just drop me an email and we can discuss after that.
Thank you very much for the nice presentation. I was wondering about the SCOMO force to combine with some carbon-based nanomaterial. Do you have any future agenda on working with that, like graphene or carbon nanotubes for some electronic or optoelectronic applications?
We are continuing the work on the carbon dioxide reduction, but we are absolutely open to put them on graphene and to put them also on carbon nanotubes. I mean, this is something, there are different techniques to do it, because you can just, for example, just support them anyway you are going for the affinity. You can also make some covalent graphene. So again, there are a lot of things to do. I mean, we can discuss design.
Sure, sure. Thank you so much. It was very nice. Thank you.
Başka soru var mı acaba? Any questions?
Okay.
I have another question just for curiosity. Those molecules individually, how big are they? I mean, in nano size, or
How
you measure your molecules, the phthalocyanine and their derivatives, and they are, I don't know if they are in the solution, they are all separated part or agglomerated. How big are they?
Big, you said?
Yeah, big, large. How large are they?
The smallest core is something like 600 gram per mole, so it's not giant. You can, depending on they can be used as the core of dendrimer, so you can make something really, really big also. It's not that small because it's a minimum of this 600 gram per mole, as I said. And then their structure makes that they are really prone to aggregation. I mean, they like to stick to each other. So this is something that we are trying to avoid. Very rarely we try to promote it, but usually we don't, it depends. So then this is then also, I would say, our job to introduce some actual substituents or bulky substituents at the periphery, or we have some strategy to do this.
I wonder that when they are in solution, I am sure there are some agglomerated particles they form, right? They packed each other.
This is what we call the aggregate. Yeah.
Yeah, aggregate. How big those aggregates?
I cannot tell you. It depends on the condition. I mean, they can be completely monomerized, for example, in THF, and you just add a little bit of water, they will be a dimer, and then they will continue. So it depends on for the aggregation, there is what I call the internal parameters, so the structure itself, and then it depends on the solvent, on the concentration, on the temperature. So there is no data to give like that. It depends really on the conditions.
Okay, thank you. Because you mentioned that there's some nanoparticles to get into the cell and everything, there's size matters on those, right?
Yeah, but then we want to have something defined. So we prefer to have the control in the nanoparticles and to inject it than to just see if it's going to agglomerate or not. Agglomeration is something that usually we don't want because it's not controlled. So.
Okay, thank you.
You're welcome.
Zannediyorum artık sonuna geldik etkinliğimizin. Hepinize katılımları için çok çok teşekkür ediyoruz. Haftaya yeni bir Nano Open seminer serimizde görüşmek üzere diyorum. Hocam tekrar katıldığınız için, paylaşımlarınız için de çok teşekkür ediyorum Dr. Fabienne Dumoulin. Tekrar görüşmek üzere. Hoşça kalın.
Görüşürüz.
Bye bye.
Bye.